Welcome to chi-squared. This is the last inferential statistic that we're going to be going over in this course, okay? Now, as stated before, the only thing that's changing when you go from inferential statistic to inferential statistic, so t-test to test difference between rho and zero, one sample t-test, independent samples t-test, dependent samples t-test, one-way ANOVA. The only thing that's changing is the sample data that you're dealing with. The sample data that you're trying to use to make a statement about the larger population. So in chi-squared, the sample data that we're dealing with are counts or frequency. So here's our example for today. Let me go ahead and read the prompt. Mr. K believed that students who read the course textbook before every lecture would pass the course more than students who did not read the course textbook before every lecture. Okay, so read the course textbook, did not read the course textbook. To test his hypothesis, Mr. K randomly assigned 25 students to read the course textbook before every lecture, and the other 25 not to read the course textbook at all. At the end of the course, he counted the number of students who passed and failed in each category. The found frequency counts are presented in the table. Okay, so red, 20 plus 5 is 25. So 25 students were randomly assigned to read the course textbook. 12 plus 13 is 25. 25 students were randomly assigned not to read the course textbook. Okay. And some of those students in each category passed and failed. So for example, out of the 25 people who read the course textbook, 20 passed the course, 5 failed the course. Out of the 25 who did not read the course textbook, 12 passed the class, and 13 failed the class. Okay, so those are our frequency counts. Let's go ahead and continue with the problem. So step one, we're going to find the expected values. So these values in black are the observed values, meaning it's literally what was observed. Of the 25 who were randomly assigned to read the course textbook, 20 passed and 5 failed. We actually observed those. These are our sample data. The first thing I want us to figure out are our expected frequencies. And essentially what expected frequencies are, if reading the textbook didn't have any sort of impact on passing or failing the class, what expected counts would we see in those cells? So as we're calculating expected frequencies, we need to go ahead and label the cells. And let me show you what that looks like. Because if we don't label the cells, it's going to be kind of confusing for us. I'm going to go ahead and use red. So we're going to label this first cell A, the next one B, C, and D. So to calculate expected frequencies, the formula is E equals the column total multiplied by the row total divided by the total n. Okay, cool. So what does it mean by column total? Okay, well, what it means is you need to find the total for the columns. So 20 plus 5, you have a column total for read of 25. 12 plus 13, you have a column total for no read of 25. For pass, 20 plus 12, you have a row total for pass of 32. For fail, 5 plus 13 is 18. You have a row total of fail that's 18. Now notice, 32 plus 18 is 50. 25 plus 25 is 50. Because there are 50 participants, right? 25 who are randomly assigned to read the textbook, 25 who are randomly assigned not to read the course textbook. Okay, perfect. So what does this look like? What I want you to do here to keep everything organized is I want you to write A, B, C, D. Perfect. So let's do the equation for A. What's the column total for A? The column total for A is 25. What's the row total for A? It's 32. And what's the total N? The total N is 50. Now let's do B. What's the column total for no read? It's 25. What's the row total for no read? It's 32. And the total's going to be 50. Now let's do it for C. What's the column total for C? It's 25. What's the row total for C? It's 18 divided by 50. Let's do D. What's the column total for D? 25. What's the row total for D? 18. Okay, so 25 multiplied by 32 divided by 50 is going to give us 16. Okay? 25 multiplied by 32 divided by 50, it's the same thing, right? It's going to give us 16. 25 multiplied by 18 divided by 50 is going to give us 9. 25 multiplied by 18 divided by 50 is going to give us 9. Okay, so once we've figured out what our expected frequencies are, we need to go ahead and add those back to the cells. So the expected frequency for A is 16. Okay, and we can just note it like this. I'm going to tell you what, and you've probably figured this out already, using different colors is going to help you out. Okay, the expected frequency for B is going to be 16. The expected frequency for C is going to be 9. The expected frequency for D is also going to be 9. Okay, good. So now that we did those calculations, I'm going to talk to you about the null and the alternative hypotheses. So I'm going to go ahead and erase this, and then I'm going to go ahead and continue. And by going over the null and alternative hypotheses, you're going to better understand the relationship between observed and expected frequencies. Okay? The null hypothesis reads, expected frequencies equal observed frequencies. Okay? And what does that mean? Okay? If the expected frequencies are equal to the observed frequencies, it means there's no relationship between the two variables. The two variables being reading the course textbook or not reading the course textbook and passing or failing the class. Okay? So these expected frequencies represent the null hypothesis. So the closer your observed frequencies are to your expected frequencies, the more likely that there's no relationship between these two variables. Okay? The alternative hypothesis is expected frequencies are not equal to the observed frequencies. Okay? If the expected frequencies are not equal to the observed frequencies, it means that there must be a relationship between the two variables. Okay? Okay, so just to reiterate, the null hypothesis is saying that the expected values are equal to the observed values. Okay? What does that mean? That means there is no relationship between reading the course textbook and passing the class. Another way of saying that there's no relationship between the two variables is saying that the two variables are independent. Okay. Okay, just to reiterate, the alternative hypothesis is the expected frequencies are not equal to the observed frequencies. Okay? So if the expected frequencies are not equal to the observed frequencies, it means there's a relationship between the two variables, between reading the course textbook and passing the class. Another way of saying that is the two variables are dependent on one another. Okay? Okay, step 3, we're gonna select our alpha level. Okay, the professional standard is 0.05, so we're gonna stay with that. Step 4, we're gonna figure out what our degrees of freedom are. So our degrees of freedom for chi-squared are going to be rows minus 1 multiplied by columns minus 1. Okay, so how many rows are there? Well, there are 2 rows, right? 1, 2. How many columns are there? 2. 1, 2. So chi-squares can be any size, but for this class, they're always going to be 2 by 2. 2 by 2 means 2 rows, 2 columns. So really, for any problem we do in this class, the degrees of freedom are all going to be the same. 2 minus 1, 2 minus 1. Okay? So 1 multiplied by 1, so there's 1 degree of freedom. Okay, perfect. Let me go ahead and erase that, and then let's figure out what our chi-squared critical is. So again, chi-squared critical, alpha 0.05 with 1 degree of freedom is going to be what? So let's go ahead and take a moment to figure out what the chi-squared critical is.
Okay, so in order to find the chi-squared critical value, you need to go to Files, Tables, and then you need to download the chi-square table. So let's identify our alpha level. Our alpha level is 0.05, and we have 1 degree of freedom. Okay, so our chi-squared critical value is 3.841.
Okay, great. So we figured out what the chi-squared critical value is. It's going to be 3.841. Okay? As always, let's go ahead and draw our picture. We'll do it over here. So the chi-squared critical rejection region, if you will, looks a lot like the F critical rejection region graphic. So let me draw it up here. So here we have it. Chi-squared critical alpha 0.05, 1 degree of freedom is 3.841. We have our little rejection region here, right? So we're going to reject the null, okay? P is less than 0.05. Okay, and we're going to retain the null on this side. P is greater than 0.05. So once again, you cannot have a negative chi-square value, just like you can't have a negative F value. Okay. So now we're going to go ahead and calculate the chi-squared obtained. The equation is this. Chi-squared equals the sum of the observed minus the expected frequency squared divided by the expected frequency. Okay, so this is actually easier than it looks. What I'm going to do is I'm going to draw up a table, okay? And all you have to do is solve the table, and then you have your chi-squared obtained. So in this table, once again, Okay, so basically, as we move from left to right, we're automatically going to solve this equation. So it's going to work out rather well. So the first thing, for cell A, what's the observed value? Okay, the observed value is in black, remember, it's 20. For cell B, what's the observed value? It's 12. For cell C, what's the observed value? It's 5. For cell D, what's the observed value? It's 13. Now for cell A, what's the expected value? We found the expected value to be 16. For cell B, we found the expected value to be 16. For cell C, we found the expected value to be 9. For cell D, we found the expected value to be 9. Okay? Observed minus expected. 20 minus 16 is 4. 12 minus 16 is negative 4. 5 minus 9 is negative 4. 13 minus 9 is 4. Okay? And then we need to square each of these values. Well, 4 squared is 16. Negative 4 squared is 16. Negative 4 squared is 16. 4 squared is 16. Okay? And now we need to divide each of these 16s by the expected value for the given cell. So I'm going to change back to blue here. So 16, right, is the top here. 16 divided by the expected value, which is 16. So 16 divided by 16 is 1. Okay, 16 divided by the expected value here. So 16 divided by 16 is 1. And then here we go. 16 divided by 9 is going to give us 1.78. 16 divided by the expected value, which is again 9, is going to give us 1.78. Now, in order to solve this equation, right, because we found the observed minus the expected squared divided by the expected, all we need to do is we need to sum the last column. Okay? So 1 plus 1 plus 1.78 plus 1.78, and that's going to give you a chi-squared obtained value of 5.56. So your chi-squared obtained is going to be 5.56. Okay, now let's go ahead and throw this onto our rejection region graphic and see whether we're going to reject or retain the null hypothesis. Okay. So look, chi-squared obtained is 5.56. Well, it's clearly going to fall in this rejection region area. And because that's the case, we know that we're going to reject the null hypothesis. P is less than 0.05. Okay, now we're going to go ahead and do the interpretation. Okay, so we found that our chi-squared obtained is 5.56, which is greater than the chi-squared critical value of 3.84. Because of this reason, our p is less than 0.05 or 5%. We're rejecting the null hypothesis, and therefore we're interpreting the alternative hypothesis. The alternative hypothesis is saying there is a relationship between reading the course textbook and passing the class. Other ways of saying that, the two variables are dependent, the observed and the expected values are not equal. Okay? So this next statement is really important, right? Because it's telling us the direction of the relationship. Okay, it's saying specifically students who read the textbook before every lecture pass more than students who do not read the textbook before every lecture. Okay, so how do you figure that out? You have to go back to the sample data to figure out the direction of this relationship. Okay, so let's go ahead and check this out, right? So of those who read, right, 20 passed and 12 didn't. So now go and take those 20 and divide it by 32, right? Because out of the 32 that passed, 20 actually read the course textbook. So go ahead and take 20 divided by 32, and you're going to get 62.5%. Okay, so of the students who passed the course, 62.5% of them read the textbook. Okay, another way to look at that is go ahead and look at pass and fail and read. So 25 students read the textbook. Okay, so 25. And of the 25 who read the textbook, 20 of those passed. So then we're looking at 20 divided by 25. Okay, 80% of students who read the textbook passed the class. Okay, and now let's compare that to the students who did not read. Okay, so 25 students did not read the textbook, and of the 25 who did not read the textbook, 12 of those passed the class. 12 divided by 25, 48%. So 48% of the students who did not read the textbook passed the class, whereas 80% of the students who read the textbook passed the class. Okay, so that's looking at read versus non-read, but let's go back to pass-fail. So 20 students who passed the class read the textbook. So 62.5% of students who passed the class read the textbook, whereas only 12 divided by 32, or 37.5%. So 37.5% of the students who passed the class did not read the textbook. So let's say that again. So of those who passed the class, 37.5% didn't read the textbook. Okay? Of those that passed the class, 62.5% read the textbook. So looking at all those different relationships, we're clearly seeing that students who read the textbook before every lecture pass more than students who do not read the textbook before every lecture. Okay, let me finish off this interpretation, but in order to do that, I need to erase this table. Okay, perfect. So the probability of the actual data obtained, so seeing that the observed frequencies are different than the expected frequencies, okay? If the null hypothesis is true, the observed frequencies are equal to the expected frequencies in the population, okay, is less than 5%. Okay. You know, I think I want to write this a different way that makes more sense. So the probability of the actual data obtained, okay, would be the observed frequencies. That's the actual data obtained. If the null hypothesis is true, okay, yeah, I think this works out better. If the null hypothesis is true, the null hypothesis is represented by the expected frequencies. So if the null hypothesis is true, it means that the expected frequencies are the population values, is less than 5%. Because of this small probability, p is less than 0.05, it is concluded that the frequencies of the population from which the sample observed frequencies were drawn are different than the observed frequencies specified by the null hypothesis. Okay, so let's go ahead and draw this out. Okay, so once again you could think of it like this. So the probability of the actual data obtained if the null hypothesis is true. So the null hypothesis here can be represented as the expected values. So we'll just draw it like that. So the probability of the actual data obtained, okay, if the null hypothesis is true, so represented by the expected values, is less than 5%. So here we got the observed values. So the probability of us getting the observed values that we got if the null hypothesis is true is less than 5%. Okay, p is less than 0.05. Okay? Because of this small probability, it is concluded that the frequencies of the population from which the sample observed frequencies were drawn are different than the expected frequencies specified by the null hypothesis. Okay, so what that's saying, again, is because us getting the observed frequencies that we got has such a low probability, we don't think the expected frequencies represent the population. Okay? We think the expected frequencies should be closer, if you will, to what the observed frequencies are like. And this last part, observed frequencies did not occur by chance in a population where the expected frequencies are true. Okay, so remember what that's like. Here, let me go ahead and erase this. You see, the observed frequencies that we got, p is less than 0.05. So if the expected values were true, the probability of us getting the observed frequencies that we got is less than 5%. Okay? So we're saying observed frequencies did not occur by chance. Okay, so it did not occur by chance. Chance fluctuations, again, are known as sampling error, right? So if we sampled from a population where those expected values are true, we would get values all around this expected value. Okay? So our observed values would be a lot closer to the expected values. P is greater than 0.05. But that's not what we got. Okay? Our observed values were so different that the probability of us getting them, if the expected values are true, is less than 5%. Okay. So the observed frequencies did not occur by chance in a population where the expected frequencies are true. Okay, so they're not chance fluctuations, they're not due to sampling error, or meaning the observed frequencies that we see are not due to sampling error. Seeing differences, not merely chance fluctuations. Okay, good, so we covered that. Okay, so that's good. We're done with that. Besides the fact that I want to show you what it's going to look like if we retain the null hypothesis. So let's go ahead and do that, and then we could go ahead and move on to the effect size. Okay, so let's say our T obtained was a 1. So a 1 would be less than a T critical of 3.84. Our P would be greater than 0.05. So we would go ahead and have to retain the null hypothesis. Okay. Because we're retaining the null hypothesis, we would interpret the null hypothesis. Okay. We would say there is, we would say there is not a relationship between reading the course textbook and passing the class. The two variables are independent. Okay, instead of being dependent or related, okay, the observed and expected values are equal, okay. So then obviously we wouldn't have this statement because we're saying there's no relationship. So we wouldn't have to say specifically, no, there would be no relationship, okay. The probability of the actual data obtained if the null hypothesis is true, this would change to greater than 5%. Because of this large probability, P is greater than 0.05, it is concluded that the frequencies of the population from which the sample observed frequencies were drawn are different than the expected frequencies specified by the null hypothesis. We would say were drawn may be the expected frequencies specified by the null hypothesis. Observed frequencies did occur by chance in a population where the expected frequencies are true. Seeing differences, merely chance fluctuations, which we have also called sampling error. So there you have it. So let's go ahead and do effect size. Okay. Now that we found that there is a significant relationship, how big is the relationship between the two variables? So we could only use this specific effect size if our chi-squared has 1 degree of freedom, which it does, so we're good. And that is phi or phi. Okay, so what's our chi-squared obtained value? Well, our chi-squared obtained value is 5.56. Our total n is 50. So 5.56 divided by 50, now go ahead and take the square root of that, and there's your answer. We're getting an effect size of 0.33. So remember, when we're talking about effect size, well, we actually don't know phi, but we do know r. Phi is equal to r. So phi equals 1 is a small relationship. Phi equals 0.3 is a medium relationship. Phi equals 0.5 is going to be a large relationship. Okay, therefore there is a medium to large relationship between reading the course textbook before every lecture and passing the class. Okay, perfect. So it looks like we're done. So be sure to email me if you have any questions. Let's go ahead and pray. Dear Heavenly Father, thank you so much for giving us this day. Lord, thank you so much for dying for us and ripping the chains of death away from Satan. So then when we die, we may be with you in your presence forever. Lord, we praise your creation. We praise every opportunity that you give us. Lord, give us the wisdom to see every breath we take, every action that we make as a way of worshiping and praising you. Lord, give us the wisdom to turn to you every day, my Lord, and ask you, Lord, what would you have me do? My life is yours. Thank you so much, Father. Thank you for giving your life for us as a love sacrifice so that we may be with you for all eternity. In Jesus' name we pray. Amen. Thank you. Have a nice evening.